In this lecture, we're going to complete our summary of nonparametric statistics by starting with a test referred to as the Wilcoxon t-test, or also referred to as the signed rank test. And this particular statistical procedure is similar to the paired samples t-test, in which there are two groups of scores that are going to be compared, but the participants or the cases engage in both measurements or in a repeated measures fashion. And as we've seen with other nonparametric procedures, the data will be ranked and the same participants are evaluated twice. So the steps involved with this process is to determine different scores for each pair of scores, and we'll see that on slide 24 here shortly. The number of the non-zero scores are then determined. So if the first score of one participant is equal to the second score of that same participant, it is a zero score and will not be used in the final tally of the numbers. The non-zero difference scores are then assigned ranks. So in a similar manner as we observed in a previous lecture with the Mann-Whitney U-test, the raw scores are assigned ranks, except in this case the ranks are assigned to the difference scores. The rank of 1 is assigned to the smallest difference, and then the ranks are moved from a smallest to largest manner. The ranks are then separated using the sign of the difference scores. And so some of the difference scores could be positive, some could be negative. The sum of the ranks for the positives are then summed, and the ranks of the negative scores ranks are then summed up. The sixth test, or the sixth step, is to determine the Wilcoxon t statistic, or what's often referred to, as we've referred to it often in this course, as the t obtained, which is the smallest of the summed ranks. And this is similar to what we observed with the Mann-Whitney U-test. It's two-tailed, so this is a non-directional type of assessment. And so there is an option where a one-tailed approach can be used, where in that sense the prediction of whether the differences are either positive or negative. But we're going to stick with the two-tailed approach here. The seventh step is to, as we've seen throughout the course, is to find the critical t-value on what's called the Wilcoxon table. And n would refer to the number of pairs. And once again, we always go with an alpha level of 0.05. The obtained is then compared to the critical, and in a similar manner as we observed with the Mann-Whitney U-test, the t obtained is statistically significant if it's less than the critical t value. And so just to review the information here, once again we have two related samples, ranked data. The parametric equivalent is the paired t-test, so that the participants are evaluated twice. And in this sense, this is the first time we're seeing that instead of evaluating the mean, we're going to evaluate the median related to these samples. So the null hypothesis states that the population median difference, we're talking the difference between the two scores, is 0, whereas in the alternative, the difference is not 0. And what we see here is a similar type of study that we observed in the previous lecture, in which participants were responding to a red stimulus on a computer screen versus a black stimulus on a computer screen, and the reaction time is measured. Now, in this situation, the same participants, rather than different groups of participants, were measured twice. And this is an advantageous type of study design, the repeated measures design, because the variability between participants is removed. And so here we see the raw scores in reaction time in milliseconds. So we see the first participant took longer to respond to a black stimulus on a computer screen than the same person did with the red stimulus, and we see a fairly consistent pattern all the way through, except for the last two participants, which had scores in the opposite directions. So the first step is to calculate the difference of the two scores of a red subtract black, and here we come up with a negative score of a negative difference of negative 220. We see a range of different scores. We have a positive score for participant 8 and participant 9. Note that participant number 10 had the exact same reaction time and generated a 0 difference, and the 0 difference would not be used in the next steps. So of all of these scores, the scores are ranked, and we see that ranking take place where the positive 10 is the first rank score, plus 50 is the next one, and then so on and so forth, and we see the score of negative 450 is ranked number 8. The ranks are then separated according to whether the difference value is negative or positive, and we see that here, and then we sum vertically, where we have the sum of the ranks on the negative side is 42, and the sum of the ranks on the positive side is 3. And so we're left with a sample size of 9 from a starting sample size of 10. So once again, with step 1, we determine the different scores for each pair. In our situation, we did a red subtract black. We keep the same order all the way through the table. We determine the n of the non-difference scores. Those ranks are then assigned to the non-different scores, and we ignore the sign of each of the difference. The ranks were then separated using the sign of the different scores. So we assemble all the negative, or the ranks for all the negative different scores, and the ranks of all the positive different scores. The sum of the ranks were then computed vertically for both the positive and the negative side. The Wilcoxon T is then determined, and we're not going to go through the mathematics in this lecture, but there is another set of equations used to determine the Wilcoxon T. The smaller of the two ranked summation scores is then obtained. So in the event that a researcher intends to go for a one-tailed approach, the prediction is whether most of the differences will be positive or negative. And so this is something that would have to be stated very early prior to the statistical analysis. The T critical value is then obtained from the table that we'll see on the next slide, the critical value for Wilcoxon T. And so it's important to know how many pairs of scores exist. And there are 9 pairs. Despite the fact that there were 10 participants, we were only left with 9 pairs of scores because there was one 0 difference score, and we're going to stick with the alpha of 0.05. And the final step here is we compare the T obtained to the T critical, and it's statistically significant if the T obtained is less than or equal to the T critical. And so what we see here is in the table to determine the critical value for the Wilcoxon signed ranks test, we are going with the two-tailed approach at the 0.05 level. Once again, even though we had 10 participants, we're left with 9 scores that were non-zero, and we have a critical value of 5. So once again, to review the null hypothesis of the Wilcoxon t-test, the null hypothesis stated that in the population, the median difference is 0, whereas the alternative, it is not 0. That indicates that in the null hypothesis, the scores, the reaction to a red stimulus is going to be the same as that of the black symbol on the computer screen. Working through the calculations, which was not done in this lecture, but there were a set of equations that were used to obtain the Wilcoxon t-statistic, and those equations gave us a value of 3. Many statistical software programs would return the same value. Note that we looked up on the table the critical value of 5. Therefore, since 3 is less than 5, we reject the null hypothesis, and we conclude that each sample, red versus black, represents a different distribution of ranks in different populations of reaction time scores. Therefore, a reaction to a red stimulus is faster than a black stimulus on a computer screen. The last 2 slides here, although we won't go through the hypothesis testing approach, but we'll just look at this from an example perspective, is in the event that we have research designs that includes more than 2 groups, specifically independent groups. And so one example here is studying the effect of post-exercise treatment on pain perception. And so our dependent variable in this example is pain, and was measured on a 10 centimeter or 100 millimeter visual analog scale from no pain to maximum pain, and the participants would just indicate on a line where they felt pain, as indicated by the numerical values. The independent variable in this case is treatment, and how that post-exercise treatment would affect pain perception. So participants in group 1 were sat in an ice bath. Participants in group 2 were provided a massage post-exercise, and of course we have a control group which had no treatment. And if you notice the nature of this design here, with our main outcome being pain and 3 levels of one independent variable, this is the non-parametric counterpart to the parametric analysis of variance approach, where we have 3 independent groups here, and those 3 independent groups are measured on the same for the same outcome. The specific test to statistical procedure is referred to as the Kruskal Wallis H-test, and as indicated, this is the non-parametric equivalent to the one-way ANOVA. Note that this is not a repeated measures design. So in this design, we have 5 participants in group 1, 5 completely different participants in group 2, and 5 completely different participants in group 3, and the numbers 40, 60, 10, 25, 30, so on and so forth, as you see in the left-hand column underneath each group, represents the score on the visual analog scale. And once those scores were obtained for all the participants, then all the scores were then ranked from lowest of 10 millimeters to the highest score of, as we see here, 85 out to 85 millimeters, and that was a rank of 15. In this scenario here, we would add up all the ranks, and the summation would then be used in a set of equations for the Kruskal Wallis test, also considering the average rank. The average rank for group 1 is 5.4. We see the average rank for group 2 is 5.8, and the average rank for group 3 is 12.8. So just making a visual observation, here we see the average rank for groups 1 and 2 look quite similar to each other, and both appear to be considerably lower than the ranks for group 3. Now, the group 3, which had these much higher average ranked scores, suggests that they had the largest measurement on the outcome variable, indicating more pain. And when we go back to the research design, we discovered that the participants in group 3 were subjected to the control condition. So they were not provided ice bath or massage post-exercise as a means of managing pain. And the ultimate question here is whether the ice massage treatment, the ice bath treatment was significantly different than the massage treatment, and we might make a subjective estimation here that they were probably not statistically significant in terms of the difference between the two, given the average value being so similar. However, we can probably suspect that they are both superior than doing nothing in terms of the control treatment. So this ends our unit on non-parametric statistics.